No sense of history.
It's like my grandfather. Don't think your grandfather.
Pokemon Go.
No!
You could get Pokemon Go,
No.
and you could take care of your Pokemon. Yes. Or Robot Dog. Yeah. Well, I don't know about the kitten. Maybe the cat. I don't know.
But why kitten is not allowed?
It's just, it'll make a mess. It'll pee and poop on the carpet.
No.
That's what they do.
Of course, I have to teach.
Yeah, so don't teach it here.
No. I mean, I teach the kitten
How to be good.
Yeah.
Okay. Well, if the kitten is very good, maybe one day.
Okay,
Maybe. But the kitten must be very good. Yeah?
Okay.
No poop, no
What?
pee. Yeah. No
So
biting, exactly, no scratching.
if I take it out, I'll give it.
How about we worry about this later? Okay, so first we have simple harmonic motion. Yes. Again, no pooping or peeing in class. Okay, fine. But at least try. Okay.
Two questions.
All right, let's have a look here. So we'll do simple harmonic motion first, and then we'll do pendulum. And if there's time, we'll have a start on the new chapter then. Okay, let's see what's first here. Here we go. So the first one, a pendulum starts at its amplitude. It's swinging back and forth. It's 5 centimeters is the amplitude. So for number one, the amplitude is 0.05 and the time is 0.5. That was way too long for a cigarette, dude. What happened?
It's like switched off halfway, so.
What, the cigarette?
Yeah, so I had to light it up again.
No, you didn't have to. You could have gone to class. Time is 0.5. How fast is it traveling after 5 seconds? So which formula do we need here? Do we need the V equals A cos or A sine? Sine, yeah. V equals A omega sine omega t. You remember this one? Now, do we know the A? Yes. Do we know the omega? Kind of. What's the formula for omega? 2 pi over t. And we have the omega here. It's 2 pi over t. But this t, what's this small t? What's the value of this small t? 5. Yeah? Okay, my calculator is opening. Does someone have this calculated?
0.01.
0.01? You didn't get this? What's it?
Sine.
There. What answers did you get, please?
0.01.
100% sure?
Yes.
You're in radian mode?
Yes.
Okay.
Is it 0?
Why you?
Why is what 0? Yeah, it should be. It should be.
You said if it's even, then it's 0. Because then it would be.
Yeah, hang on. Let me think. It's after 5 seconds, which is 10 half seconds. So it should be. It should be nearly 0.
So can't we just write 0?
Yeah.
Without any calculation?
No, I wanted you to practice using the formula. I think for next year I'll change the time so it's not 5.
Oh,
Yeah.
0.01. But what happens if I give 0.01? It is okay.
Maybe. Maybe. Let's go on. That was a bad question. Number 2. 50 kilogram mass is pulled at the end of a spring. The spring's at rest. The gal pulls it down a distance of 10 centimeters. What did I say the mass was? 50 grams. And releases, and the time is 3/4 of a second. And I would like to know first the omega. What formula should I use here?
T.
2 pi over t, yeah. Which is 2 pi over 0.75, which is what exactly?
S-I-3-S.
8.38, yeah. What's wrong? 8.38 radians per second. B. What is the acceleration after 1 second? Yeah, which formula to use here? Which one? Yeah, but which formula to use? The A after 1 second. See, I think what you need to do first is you first need to find the S after 1 second.
Minus omega f.
Yeah, but first you need to find the S before you can use that. So the S or the X equals, now is it A cos or is it A sine? Cos. Hey, no fighting now. Okay, what's this please?
Minus 0.05.
Minus 0.05? Because it starts on the outside because she pulls it down. Yeah. Right, so now you were saying the formula is A equals minus omega squared S. And we know the S now and we know the omega. So it's 8.38 squared times 0.05. The minus and minus cancel. Thank you. 3.51. Like that. Question?
Are you sure it's 0.05?
No, I got this number from someone. I think I can trust her. Okay, and I think I can trust him. But just to be sure, we'll double check. Now, I first must put my calculator in radian mode. 0.1 cos 8.38. Their story checks out.
How did you put your calculator in radian mode?
Shift mode 4.
So it has to be in radian.
Yeah. Has to.
I got the same.
Can we change
No, don't do this.
But not a USB.
Don't.
You can, but
Don't. It's too risky. You don't know what you're doing. I wouldn't trust you to do it that way. Just do it this way. Okay, yeah.
But no, change your mind.
Part C. What is the force after 1 second? What's the force after 1 second? So let me just draw that to help. Is the ball moving up or down after 1 second? What do you think? Yeah, she let go, she pulls it down and let go and it is moving up. And we want to know what the force is. Well, that's easy actually because we can just use Mr. Newton and his MA. Do we know the M? Yep. What is it?
0.05.
50 grams, isn't it? And we know the A. So I even have this. I have this right here. Its net force is 0.176 newtons, we'll say. Okay?
Not too small? Oh, okay.
It's a very small mass, so.
We don't consider anything that's going the other way, like gravity.
No, because I specifically used the word net force, the total force. Newton's F equals ma gives us the total force. I didn't care about how much of it is gravity and how much is from the spring. I just want to know the net force. So in this case, I didn't need to, what you're thinking of, look at the two. Is the force upwards or downwards? It's upwards.
Why do I do up?
No.
Oh yeah.
Listen. No, actually, I'm not convinced it's positive. Faisal!
Yes?
I have punished you by removing all but one of your questions. You now only have one question you can ask me. This has been your punishment. Right.
Feels like you're treating yourself.
If I benefit from it, okay, so she pulls it down, and I know it's a bit confusing, but it goes up, down like this. If you look at what I took for the A, here, the X is A cos omega t. When the t is 0, what's X?
0.
No. Cos 0 is 1. So when the t is 0, X is A. Can you see that? Yeah. So because I didn't put a minus sign here, but it's starting from the bottom, I'm doing this problem.
Now it's here.
This is a plus and this is a minus. Because I never put a minus in at the beginning because it's starting from under the origin. So it means my signs are backwards. So, because the F is a plus, that means the force is actually heading down.
This is down.
Yeah, I'm saying the answer is down.
Oh, this is for C?
No, this is, is it for C? No, for D.
Yeah, I took the other way around, so.
Did you get an answer of down?
No, I took the down as negative.
Okay, so then your answer here should be negative then.
Yeah.
Yeah. And finally, for this one, E, now we have to look at the two of them. What is the force the spring is providing? So there are two forces here, one from the spring and one from the weight. Which one is bigger?
The one from the spring. Because the weight is not falling.
Try again and take a moment.
Depends on the time.
At this precise moment, after 1 second.
Wait.
Okay, so final answer, is it acting up or going down?
Down.
Oh.
The spring force is going up.
No, I want to know which force is bigger, the up or the down.
The down is bigger. Because it's going down.
No, the up is bigger because it's going down. As it's going down, it needs to be decelerating. So the force must be acting upwards, like a brake.
Yeah, but it's still going down, it's not going up.
True.
So the force that's pushing down is more than the force that's pushing
Oh, Faisal. If I push this to you, which way is it heading? To you. Which way is the friction force acting?
It's disappearing if your hand is pushing it to me.
Yes, true. But don't worry, it's cashless. So if I'm pushing this to you, the friction is acting not to you but to me.
Correct?
Yes. So when the ball is falling down, it's decelerating, so the force is acting up.
Yeah, but the force of your push is more than the friction. That's why it's coming to me.
No, I only push it at the beginning, but as it's moving, the only force acting on it
It's back.
is backwards. So Because it's moving down, the force is acting up. Because you know for this motion, as it moves down, it's braking. It's coming to rest. And then what will happen? It'll snap back up. So as it's dropping, this force is trying to win. It's slowing it down. If you didn't get that, that's okay. If you had it backwards, you're only going to have the wrong sign. So this one should be bigger than this one. This one is the force from the spring, and this one is the weight. So the force from the spring minus the weight force, what does that equal? Well, that's equal to the total force, isn't it? The up minus the down. That's how much I have in total. Do we know this force? Yes. Do we know this one? Yes. Can we know this one? Yeah. So the force from the spring is equal to the weight plus the total force, which is equal to mg plus 0.176. Um, 0.667 is the force. This protein vanilla milk is not quite the same as coffee. Still nice though. Okay. Tree now. A 100,000 kilogram train has a soft bumper. The bumper is to absorb any shocks. When the train is parking, its bumper hits the wall. It takes 250 milliseconds for the bumper to fully compress 2 centimeters, and a further 250 for it to decompress the same 2 centimeters. When the bumper is fully depressed, it has potential energy stored in it. How much energy, and where does this energy come from? So you have the train here, and the train has a little bumper on the front. So when it parks against the wall in the train station, in the garage, the bumper will gently push against the wall, and the springs will compress. This is 100,000. Okay, so we know how much the springs compress. That's 2 centimeters. We also know the time. We can work that out. What's the time?
Centimeters only?
I thought.
Oh,
2
2 centimeters.
I,
Yeah, it's like the amplitude. Yeah. Yeah, so actually I'll write in A. What's the time?
0.0025.
You might have too many zeros there.
No, it's milliseconds.
250 milliseconds, yeah.
Yeah.
So what's the periodic time here? 0.25. I don't think so. I think it's going to be 0.5 because the time for one cycle, yes. The bumper comes in, look. The bumper comes in. Look, Andrew. The bumper comes in, decompresses, that takes 250 milliseconds. Compresses, and then decompresses, that takes 250 milliseconds. So one cycle is 500 milliseconds, which is half a second. Okay. Now that's good because that gives us the omega. What's that, about 12 or something, isn't it? At 12.57 radians per second.
Can you say again the T?
Yes, this is the bumper. The train comes along, hits the wall, 250 milliseconds, 250 milliseconds. The time for one cycle is 500 milliseconds. Yeah? Okay, now. Yeah.
And for the
250 milliseconds to decompress.
yeah, further
What do you think further means here?
more
More what?
more than 250.
No, I'm saying it takes 250 and another 250. Yeah. Okay. What is going on over there? Are you sure? My teacher senses are telling me that it's not true. Right. We have the formula for potential energy for the spring. Do you remember it? I think it's something like a half omega. Oh, I can't remember what it is. Omega squared S squared. Yeah, and in this case the S is the amplitude. So it's a half 100,000 12.57 squared 0.02 squared. A half times 100,000 times 12.57 squared times 0.02 squared. 3160. Not as big as I thought, but pretty big. Yeah, question?
Is the amplitude and the displacement the same thing?
Yeah, well, the displacement is the amplitude. You're looking for the energy when it's fully compressed, so it's the same in this question. What did I say the answer was? 3160 joules, or 3.16 kilojoules. Well, that's a lot, I suppose. So that's how much energy is stored in the bumper. Where did this energy come from?
Potential.
No, this is potential energy stored in the spring.
Kinetic energy from the train.
The kinetic energy. The train was moving before it hit the walls. Yeah. Just like that. Okay. So the answer for the second part is from the kinetic energy.
I don't understand.
Give me a specific point I can address.
From the kinetic energy.
So the spring gets compressed. When a spring is compressed, there's energy stored in it. We know that energy has to come from somewhere. Where did it come from? The train was moving, so it had a kinetic energy. When it hits the wall and stops, it no longer has this kinetic energy. It was that kinetic energy that became the energy in the spring. The kinetic energy of the moving train became the spring's energy when the train was brought to rest by the spring.
Will a 0.02 2 centimeter spring stop a train? Is it possible?
But I never told you how fast the train is moving. So if the train, if the train was going quite fast, it will not. But I'm just picturing a train that's parking, and you know when it parks, maybe it bumps into the wall. That's all I'm picturing. Maybe.
Not go to the right one.
No. Okay. Can I continue with the next one? Yeah. A spring displaced a distance of 5 centimeters from equilibrium will vibrate with 2 hertz. How fast is the spring traveling after 0.7 seconds if it was displaced by a distance of 10 centimeters instead? Okay, so what you have here is you have a spring and its frequency is 2 hertz. So what does that mean if its frequency is 2 hertz?
2 cycles a second.
2 cycles a second, yeah. And its amplitude is 5 centimeters. So when it's displaced 5 centimeters, when it's pulled down 5 centimeters, it moves with this frequency. Then somebody comes along and pulls it down 10 centimeters. How fast is the spring traveling after 0.7 seconds if it was displaced by a distance of 10 centimeters instead? So you pull it down by 10 and it starts moving up and down like this. Okay, so what we'll do is, let's just look at this situation on the left first. We know the F. The F equals 2. So what does the T equal? 1 over 2, which is half a second. Yeah? Now, what happens if somebody pulls it down further? what happens to the time? Yes?
It's,
No, do you want to?
Trick shot.
There's no change.
Thank you, thank you. I've got one person who's focused. There's no change in the time. So when you move to this picture, even though it's pulled down more, the time is still half a second, which is great, because it means the omega now is 2 pi over 0.5, which is 12.56 radians a second, I think.
So,
Yes?
5, 7.
Oh, well, excuse me. 5, 7. Now, we want to know the time after, the velocity after 0.7 of a second. Am I using cos or sine if I pull it down to the bottom and release?
Velocity.
Sine.
Sine. A omega sine omega t. Do I know A? Yes. Omega? Yes. Omega? Yes. And t?
Yes.
What is this t?
Oh,
0.7. Yeah. So 0.10 times 12.57 times sine 12.57 times 0.7, and I get 0.736.
I have a question.
Now this is going to be it.
Yes.
Make it good.
Yeah.
Okay.
We're dealing with springs, so if we increase the amplitude, it will not change the time period.
Correct.
Is this for all types of simple harmonic motion, or is it only for springs? Like if we increase the amplitude for a pendulum, let's say, will the time period be the same?
It's definitely the same for springs, rubber bands, things that are elastic. But it might not be the same for every type of simple harmonic motion. Like, for example, I would have to think about if this still holds true if we're talking about atoms vibrating, because if you if you do something to try and increase the amplitude of the molecule, you might affect the molecule in such a way that it no longer behaves as it was behaving. It might not even move in simple harmonic motion anymore. You might have separated the molecule by trying to increase the amplitude, you know. So it's going to be at least true for any stretchy material like a spring, rubber band, things like this.
Not for a pendulum.
For a pendulum, the time will be the same, because the time formula does not have amplitude in it.
Yeah, I'm thinking of that, but like in reality, if we
In reality, it will have a small effect on it. We do not consider this effect. Okay, actually I think the pendulum is what we're going to do next. Yep, that's it. So on to the next homework.